I'm going to talk about advances in photovoltaic energy conversion. This work was partially supported by National Science Foundation. And this is the group. I'm not going to spend too much time on it, but it's a truly international group. And Nishta used to work with me. She's from Rajasthan. Berang, he has also left. He is from Iran. Max is an American. Wai Leung is originally from Hong Kong, but now an American. Then behind them is Ben Reichert. He's an American. Harsh is from ICER. He's from Bangalore. Junha Zhu is from China. Nancy is a group secretary. Sabah is from the country of Georgia. Ranjit is from Kerala. And he went to Indian Institute of Science for a PhD, and he's my postdoc. And Polly is from, Laila Polly is from Bangladesh. It's a very international group. So I'll start by introducing to photovoltaics, emphasize the physics of PV, the status of various photovoltaic technologies, talk about new materials, perovskite solar cells in particular, and then discuss about fabrication techniques, physics of perovskites, and future research needs, which offers a lot of opportunities for people like you. First of all, photovoltaic energy conversion. It converts photons into electrons. It's a major solar power industry. The approximate volume of photovoltaics installed in the world is 770 gigawatts. That's equivalent to 770 nuclear power plants. That's huge. Annually, it's $200 to $300 billion per year. That's enormous. It's growing at 40% per year, 40% growth rate per year. Just look at the growth curve from 2006 to 2020. More solar plants are being installed than any other power technology. And of course, China leads. The reason for more solar plants is because eventually economics has to win out. It's because the cost of solar in appropriate locations beats everything else. On the left is the map of Chile, the country of Chile. In the Santiago, there's the capital, Valparaiso, their main port. So the population density is here. But north of them is the Atacama Desert. It's the driest desert in the world. It really is. It just does not rain, period. So companies have set up solar photovoltaic plants here, and they're transmitting electricity to Santiago and Valparaiso. The cost of that electricity is 2.9 cents a kilowatt hour, half the cost of solar, half. So of course the countries would go for solar. Why not? In the chart on the right shows the cost of solar in US cents per kilowatt hour for different countries. And in places like Dubai, it's also in between 3 and 4 cents a kilowatt hour. It beats everything else. And it'll beat everything else in Rajasthan and northern Gujarat and Kutch. The reason for that is the dramatic reduction in cost. It started out in 1977 at $76. I started working even before that, 1973. And the cost was over $100 per watt, not per kilowatt. Now it is down to 30 cents per watt. It has come down from 76 to 30, a factor of almost 300 over the period of, 40 years. And the PV module prices, it shows the drop in the right slide. It's a busy curve. I'm not going to emphasize it. What I'm plotting here is cell efficiency, percentage versus year. For different technologies, a whole bunch of other technologies. For example, this highest efficiency technology is the multi-junction solar cell is at 47%. 47% of solar energy is converted into electricity. That's damn good. Crystalline silicon is somewhere around here. So it's around the best in crystalline silicon is about 27%. And this new material, perovskites, which is this curve, it only started in 2013. And it was like 10, 12%. And now it is at 24, 20, almost 26%. Look at the growth rate for the perovskites compared to this group. I mean, it was almost a vertical curve for a while. Much faster than anything else. So first question is, why the efficiency is so low? For comparison, coal burning power plant is, the new coal burning power plants going up in India are about 42, 43%. The best coal burning power plant is somewhere around 46, 47%. The nuclears are much lower, they're only 33% efficiency. Efficiency of converting heat into electricity. Here you are converting solar photons into electricity. So you really don't go through the second law of thermodynamics unless you count the temperature of the sun. If you look at Carnot efficiency and count the temperature of the sun at about 5,600 degrees Kelvin, then the efficiency, the Carnot efficiency would be in the 95, 96%. So why is the efficiency of silicon, for example, only about 25, 26%? Well, what's a solar cell? It's a p-n junction. Light generates electrons and holes. The built-in junction field separates electrons and holes. As soon as you separate a charge, you get a voltage. Hence the term photovoltaic or PV. You connect an external circuit and a current will flow. Here is the energy band diagram. The left side is P, the right side is N. So light generates this electrons and holes. It generates electron-hole pairs. Holes, the lowest energy state is over there, so the holes go over there. The electron comes over here. If you now were to connect an ammeter, you'll get a current. If you connect a voltmeter, then the electrons will accumulate on the right, holes will accumulate on the left. Again, separation of charge, voltage. This shows the schematic diagram of a solar cell. There's this for silicon, N-type silicon, then P-type silicon, a back contact and a front contact. Light comes in here. Most of the area is open to light. Photons are absorbed, electrons and holes are generated. You connect a load outside and the current will flow. So let's look at the working principles. You first have the diode IV curve. Then you get light generated current. The light generated current is the reverse current. Holes are going from N to P. That's a reverse current. So you can say a diode, a light generated source is connected across the diode and it immediately shifts the IV curve down. It's the linear transformation of this dark IV curve. And so you get an IV curve that looks like this. So you get high current here, which of course makes it a terrific photodetector. Every single, in your camera, every single pixel element in the camera is a photovoltaic cell. It's a silicon photodiode. It's capturing photons and converting them into electrons. So you have this IV curve. You get a lot of current at short circuit, and if you open circuit, you get a lot of voltage. Obviously, you want power, so you will go somewhere along the IV curve, and the maximum power point would be around the knee of the curve. On the right is the equivalent circuit of the solar cell. A light generated source in parallel with the diode. So let's look at losses. Solar energy is distributed in energy. Solar radiation is distributed in energy all the way up from 350 nanometers out to several micrometers. It's not monochromatic. The peak of solar radiation is somewhere around 600 nanometers, 550 to 600 nanometers. The maximum energy is in the green at about 530, 540 nanometers is where the maximum energy of the sun is. That's why your eye is most sensitive to green. Evolution will guarantee it, that your eye would be most sensitive to green. And we cannot see much beyond 700 nanometers. That's the infrared. Of course, if you're a tiger or a leopard, you will definitely be able to see at night because you hunt at night. The leopards certainly do. So they can see very well at night, whereas we cannot. Now, if the band gap is too low, we can absorb photons but lose the thermodynamic energy. If the band gap is too high, we won't absorb photons. So intermediate band gap is where you can absorb enough photons and not lose thermodynamic energy. And so the best efficiency, gallium arsenide is like 29% and silicon is like 26%. What do I mean by thermodynamic loss? A high energy photon, excuse me, will excite an electron from the valence band to high above the conduction band. This energy is lost in lattice collision. So if you use a very low band gap, you have a lot of energy loss. A lot of energy loss if you use a very low band gap. If you use a very high band gap, you don't absorb. So how do you get around this loss? Before that, so there's something called a Shockley-Quasar limit, which plots the thermodynamic efficiency as a function of band gap energy. And that curve is the curve that takes account of the various absorptions in the in the atmosphere. And so the maximum efficiency is somewhere around 32, 33%. And gallium arsenide is doing awfully well. It's coming to 29%. And the peak in energy is somewhere around 1.3, 1.4 eV, which is gallium arsenide, indium phosphide. So they are the ideal materials for a solar cell. Silicon at 1.1 eV has a lower efficiency than gallium arsenide would. That is for concentration. If you concentrate sunlight, then the efficiency goes up. Very simple reason. The ultimate loss from a solar cell is the radiative loss. The electrons and holes will recombine and there'll be a radiation loss from it. Now, radiation loss is proportional to area. So if you use a large area of a lens, you get lots of sunlight, but the radiative loss is limited to a small area. Hence, the efficiency goes up. It would be a function of logarithm of the concentration. And that's people are going for concentrator cells, certainly for space. Now, the potential efficiency of two-cell tandem, you can I guess I don't have a slide on tandem. The way you can get around this problem is to combine two solar cells optically in series. A high band gap cell is the first cell and a low band gap cell is the second cell. If you do that, you minimize the thermal loss in the first cell, thermodynamic loss in the first cell, and thermodynamic loss in the second cell, because the first cell will absorb the high energy photons and the second cell will absorb the low energy photons. So you will optimize photon absorption and at the same time minimize the thermodynamic loss. So this is called a tandem solar cell. And one can plot efficiency contours for various combinations of a top band gap solar cell and a bottom band gap solar cell. we want to be in the violet region. Well, a very good solar cell for with the top band gap is the perovskite cell at about 1.7 eV. And then the bottom can be crystalline silicon or copper indium selenide at 1.1 eV. If you do that, you're coming up here, which is greater than 45% efficiency. Thermodynamic. You do multiple cells, the efficiency keeps going up. If you have 4 and 5 cells in series, the efficiency keeps going up. And indeed, National Renewable Energy Lab in the US has produced 47% efficiency by combining 6 cells optically and electrically in series. Yes, a very nice idea, but very expensive. Who loves it? The Air Force. Why? Because for the Air Force, the determining cost, excuse me, is the cost of the launch of the solar cell. It costs over $1 million per kilogram. Over $1 million per kilogram of weight. So if you can reduce the weight while producing the same power, it pays you from a launch cost viewpoint. So the Air Force wants the highest efficiency it can. And there are lots of people in India also working on high efficiency solar cells. And so is National Renewable Energy and US Air Force, and I'm sure Chinese Air Force. But for commercial applications, what you want is a nice, reliable, low-cost bottom cell on which you can put on a thin film of another material with the right band gap. If you can do that, instead of 32%, you're going to get the thermodynamic efficiency of greater than 45. That's a 50% increase in efficiency. 50%. Instead of 22, 23% panels, you will start getting 35% panels, commercial panels. Again, a 50% increase in efficiency. Why does efficiency matter? Because of this. The photovoltaic system cost is not only the cost of the PV module. PV module itself is area dependent because you've got glass, you've got encapsulants to keep away the moisture for 30 years. 30 years, you have to keep the moisture away. You have a whole bunch of solar cells in series, you're generating hundreds of volts, and any moisture gets in there, forget it. You're going to get electrochemical corrosion of your metals, of your metal contacts. So you have to keep the moisture out. And those encapsulants cost a lot of money. DuPont has an entire division which makes somewhere around $10 billion for DuPont per year just from selling encapsulants for solar cells. So encapsulant cost is important, area cost is important. Then you have the structure cost, the field structure and the field wiring. Less the area for a given power, less this cost. So this cost is huge. And then you have electronics, which is not area dependent, but these two are the major drivers. And as a result, about 85% of the cost is this guy's and not the photovoltaic material per se. So you increase the efficiency by 50%, you're reducing the 90% of the cost by 50%. Not bad. Now, what materials can we use in tandem with silicon? You must be able to deposit on silicon. Let's face it, for the foreseeable future, silicon is going to be the king. Many people have tried to displace silicon and nothing has worked. Nothing. Silicon beats everybody else because it's so low cost. You must be able to deposit on silicon, which is the material that you deposit on has to be polycrystalline. Though gallium arsenide phosphide, single crystal may be possible from lattice matching considerations. And people are working on that. Perovskites have the right band gap, and they are a polycrystalline thin film. They're only 1 micrometer thick. That's it. And the grain sizes are a few micrometers. The other possible material is cat selenide, which is also polycrystalline with the right band gap, or you could use zinc cat telluride. In this talk, I'm only going to talk about perovskites. Here are some IV curves for perovskites. And above is a band diagram of the different layers that go into perovskite. There's perovskite. You can use a P layer, heterojunction layer, or P3HT, poly3xethiophene, or you can use PTB7, or you can use a whole bunch of other organic materials. You can use PTAA, you can use a PDOT. And this curve shows the increases in efficiency. This was only up to 2017, where they had reached like almost 20% efficiency. Now the efficiencies are even higher. Look at this. Look at the curve for efficiency of perovskite versus year. It has shot up. It is now up to 26%. I should have put the new chart in there. It's astounding. That's why everybody is interested. So what material is this? It's an ABX3 material. A is usually, but not always, an organic molecule, methylamine or formamidinium or a whole bunch of other materials. So they will do is formamidinium iodide or methylamine iodide. Those are the two most popular ones, but they're using other ones too. Or you can use bromide or chloride. B is a lead or tin. Not tin by itself. It's usually lead or lead-tin combination. And X is an halide, iodine, bromine, or chloride. It's a crystalline material, and it forms at 100 degrees centigrade. At 100 degrees centigrade, it crystallizes. That's the crystal structure, basically a cubic. At the center of it is lead. Those green balls are the halides, iodine, chlorine, or bromine. And those at the corners of the cube is the methylamine or formamidine, or inorganic material like cesium. People are interested because of this extremely good absorption coefficient. This absorption coefficient versus wavelength. Perovskite's absorption coefficient is outstanding. Over the most of the photon range, it is 10 to the 5 per centimeter, which means that the absorption depth is only 10 to the minus 5 centimeter, 10th of a micrometer. So a micrometer film will certainly absorb almost all of the photons until you get to the band gap. This is the band gap out here. This is outstanding. What appears to be unique for perovskites, very high absorption coefficient, very high diffusion length. You must be able to collect the electrons in holes. Or the depletion width. The depletion widths are also in the range of a micrometer. So you're going to collect the electrons in holes. You don't need, unlike an organic photovoltaic where you need a type 2 heterojunction to separate the electrons and holes, because the dielectric constant in organic materials is low, the dielectric constant in perovskites is very high. So it separates the electrons and holes. The exciton binding energies are in the range of 10 millielectron volt, which means the heat will break them. Band gap accurately controlled by changing the halide from 1.5 eV to 2.2 EV. So visible LEDs are possible. And indeed, one of your colleagues at IIT Bombay, Dinesh Kabra, is working on visible LEDs using perovskites. And the lead, in principle, can be replaced by tin or germanium. And if you can do that, there's an environmental benefit. In principle, so far it hasn't worked. So there's the research to be done there. Non-lead perovskites. Deposition techniques are simple. You can do solution growth, sequential evaporation, or co-evaporation. What you do is you spin coat, you literally take a pipette and fill it up with the solution, and you just spin coat on an appropriate substrate. The substrate could be glass coated with an ITO, with an appropriate P layer deposited. Then you spin coat the perovskite solution, you spin it, and then you heat it up at 100 degrees centigrade, and the perovskite forms. That's it. Or you can do sequential growth, evaporation. You can evaporate lead iodide and then subject it to a vapor of methyl ammonium iodide in a sealed graphite boat, and the MAI will react with the lead iodide and form the perovskite. And we developed this technique. Or you can do co-evaporation of lead iodide and methyl ammonium iodide at the same time. This is what Snate did in his seminal 2013 paper, which basically gave rise to the field. Henry Snate at Oxford. The device is a superstrate device. Light is coming in from the bottom, glass coated with a transparent conductor, with a photovoltaic cell and a back reflector. Nice thing about perovskite, because it's a low temperature deposition, it can be put on the plastic film, which means you can bend it. It's flexible. The important thing about the device physics, and device physics for any cell is important. The important thing about the device physics is that it's a double heterojunction cell. There's a perovskite in between. Those values are the values of electron affinity and valence band. And this is a 1.6 eV material. So you put in a material which reflects holes. Holes come in here, they're reflected, but the electrons can be transmitted without any significant barrier here. And materials like titanium dioxide will work, N-type CDS will work. And similarly, to collect the holes, you would want a material such that the holes can be transmitted, but the electrons that come in here are reflected back. They can't make it up there. And the materials would be P3HT, spirometad, PTA, a whole bunch of materials work, and inorganic materials like molybdenum oxide or nickel oxide. This is our co-evaporated cell. It was about 16.4%. The best efficiency for a co-evaporated cell is about 18%. The nice thing about evaporation, by definition, it's a process that's widely used in industry. For example, all the auto companies coat your windshields with a thin layer of ITO or something else using sputtering, large area vacuum deposition techniques. All of your windows are coated this way, the automobile windows, front, back, and the side. And what we are showing here is the exceptional reproducibility of evaporation. I mean, every cell is essentially the same as the other. When we use PTA, liquid deposited, champion efficiency is about 18.5, 19%. This was done by one of my students from Bangladesh, Istiaq Hossain. Can we have non-organic perovskites? Yes, replace the MAI with cesium. And then you get cesium, it should be cesium lead I3. This is our cesium lead I3, vapor deposited at 100 degrees centigrade. The efficiency is 12%. The band gap is precisely where we want it, 1.74 eV to match with silicon. And the curve on the left is the corner efficiency curve. Perovskites in general have a very low mid-level defects. Mid-level defects in the range of 10 to the 16th per cubic centimeter, which is fine. If they are 10 to the 18th per cubic centimeter, There'll be too much recombination of electrons and holes, but they're not. The trouble with perovskites is that it's not an electronic material. It's a combination of an electronic and an ionic material. It has mobile ions. Which ions? Iodine. You literally have mobile ions in there. It's an interesting experiment done by my friend Jinsang Huang, who is now at North Carolina State. No, it's at UNC, University of North Carolina. And he was at Nebraska before. And what it shows is you can take a device and have with two contacts, you sweep the voltage one way, you get one curve, and then you sweep it back, you get another curve. Why? Because there are mobile ions which are screening out the electric field. And this is the most definitive evidence of that. What they did was to take a perovskite, a plus contact and a minus contact. They took a microscope and then they scanned the whole sample as a function of time. After 45 minutes, you begin to see something there. After 110 minutes, this interface has changed. Mobile iodine ions, which are negative, have all gone up there. And you can see them. Why are they made mobile ions? Because production of breaking of methylammonium and iodine bond only requires 80 millielectron volt. That's 3 kT. Which means if you're 10 to the 22 is the density of MAI that you start out with, 10 to the 22 per cubic centimeter, you're going to have 2 times 10 to the 20 when those ions are separated. That's a lot of ions. It's a hell of a lot of ions. It's more than electrons. So it's both electronic and ionic conductor, which leads to instability because of light. One problem is hysteresis. Again, you take the IV curve, you measure from open circuit voltage to short circuit current, you get that curve. Then you try to go in the other direction and you get that curve. Because iodine ions have moved and have screened out the potential, screened out the junction field. We'll come back to the ions. Another major problem is that the material is thermally unstable. And we can see that by looking at the X-ray spectrum of the perovskite. The blue curves are the original X-ray spectrum, intensity versus angle. When you heat it at between 85 and 100 C for 24 hours, the peaks come down and another peak appears. This is a lead iodide peak. The material is decomposed into lead iodide and MAI, methylammonium iodide. It is decomposed at 100 degrees centigrade, 24 hours. Bad news. Same thing happens if you use formimindium iodide instead of methylammonium iodide. A little more stable, but it decomposes at 125 C. Now you'll say, why do I worry about 125 C or 100 C? IIT Bombay has measured the temperature of a silicon solar cell when the outside temperature was 40 degrees centigrade. The temperature of the solar cell, the highest they measured was 86 C, at 40 C outside. Now you know that every single year in Rajasthan, the temperature exceeds 50 C. There is not a year when it has not exceeded 50 C in some areas in Rajasthan and Kutch. So you take IIT's data, with the cell temperature is going to be at least 96 C. If you have material that decomposes at 100 C in 24 hours, that's not any good. Even 125 C, not very good. That's only at 24 hours. What would happen over 20 years? It is definitely going to decompose. which in the efficiency is going to drop significantly. So we need a material that does not decompose until much higher temperatures, like 200 C. We have developed such a material. It's cesium, lead, iodide bromide, or cesium lead bromide. There's no organic molecule in there. No organic molecule. Here is the X-ray spectrum. The bottom is before the as grown, and the top is after annealed at 300 C for 24 hours, not 100 C. There is no change. There is no lead peak coming up. There's no lead iodide peak coming up here. None, zero. This material is stable at 300 C. That's the kind of material one needs to pursue. Nice thing is this material is also stable against moisture. We can leave it out, nothing happens. So let's look at light-induced instability. There are two. One is the ion decomposition of the material into ions because of light, and the other is trapping of the ions at the interfaces. We have a very nice apparatus, probably unique in the world, where we can shine high intensity, full spectrum, solar spectrum, so there's ultraviolet in there. And we can put the solar cell up there, and there's a mirror actually, solar cell sits down there. And we can have the solar cell at different temperatures and do all of the measurements in situ, and the chamber is just filled with nitrogen. We evacuate and fill it with nitrogen. So there is no influence of moisture or oxygen. It's only light. We keep them under constant illumination, and we can go up to 10 times sun intensity. We put a lens in and we can go to 10 times sun, which is good. First question we asked ourselves is, I showed you this curve earlier, is the material, this is not the lead, this is not the cesium material, this is the lead iodide material, or the MAI material. And question we asked ourselves is this material stable? Are the mid-gap density changing? No, mid-gap density is not changing. And then we observed this very interesting pattern. The black IV curve out here is the original IV curve. As soon as you expose it to light, the voltage goes up. As soon as you expose it to light, the voltage goes up. Then you turn the light off. You can let it shine for 100 hours. You shine the light off, and this curve immediately goes to the green curve, immediately. And then it slowly recovers back to the black curve. What the hell is going on? It never happens with silicon, never happens with CIGS, never happens with telluride, never happens with gallium arsenide, because they don't have ions, and we do. So the model is light generates more ions, both positive and negative. The ions influence the electric field and built-in voltage, and hence the depletion width. During degradation, electrons and holes recombine with the ions, which is a loss in current. Electrons will recombine with the positive ions, holes with the negative ions. During thermal recovery, the ions recombine and neutralize and back to inertia. So let's see what happens in short circuit current degradation. Why does the current go down? Well, this is the original perovskite under thermal equilibrium. The positive ions have the mobile positive ions in the material have gone to the P contact, which is negative, and the N contact, which is positive. You shine light, you're under open circuit voltage, so the field has gone down, the ions are diffused, and you're creating more ions by light. And we can plot ISC divided by ISC initial plot it against 1 over relative ion concentration, and we get a linear curve going through 0, 0 point. Saying indeed, light generated ions are causing recombination. Now, why does the voltage initially increase? Just after fabrication, you had the positive ions will go towards the N side or towards the PTA, towards a P contact, which is of course negative, N contact is positive. So positive ions will go there, negative ions will go there. They're going to give rise to a field between positive and negative, which is going to reduce this field. So there's a reduction in built-in voltage, hence a reduction in current, a reduction in voltage. There. So because of ion migration, you have an increase in voltage. When you are under open circuit or near full power conditions, which is close to open circuit, the field has been reduced, so the ions have moved away from their respective contacts. They are out here, so you don't have a reduction in built-in field, so you have an increase in built-in voltage, increase in open circuit voltage. And you can see the influence of ions. If you plot dark IV curve before and then immediately after exposure, you don't get zero current at 0 volt. You get zero current at about 0.25 volt. And at 0 volt, there's a finite current, a negative current. Why is there a negative current at 0 volt? That's very strange. Because the iodine ions are moving. And over a period of time, this current reverts back. If you wait, this IV curve reverts back to this one. You can plot. You can take this ion current, study its behavior, measure it as a function of time. The computer will do it for you. And that gives you the integrated charge density. Here is the current density versus time. And the area under that curve tells you how many ions you generated. By light. I'm going to skip this. But maybe I'll keep it. You can change the stoichiometry ever so slightly. Instead of lead iodide to MAI ratio of 1, you can change the ratios. And all of the solar cells have approximately the same efficiency. But the short circuit current degradation is very different. The least degradation, that's the initial short circuit current versus time. The least degradation comes around when you have 5% excess lead iodide. We don't know why. That's what the experimental result is. Now let's talk to interfaces. Interfaces can trap ions. There's a difference between using PTA versus nickel oxide. The left curve is a curve because of the short circuit current degradation on that's the short circuit current, that's the efficiency. Short circuit current degradation and when PTA is used versus when nickel oxide is used. Much less with nickel oxide than PTA. Interfaces make a difference. A very interesting thing that happens is we made a solar cell where between the N layer, which was PCBM, and the aluminum contact, normally you just have PCBM and aluminum contact. We put in 2 inorganic layers, N-type CDS and zinc oxide. The purpose of that was to prevent the ions coming from the perovskite and going through the PCBM and affecting the aluminum contact. Those inorganic layers would seal up the ions, would prevent the ions from going there. We made two cells, one with CDS, one without CDS, and similar IV curves. We look at the degradation, very similar. But all of the solar cells can be annealed back to their original conditions. You can drive the ions away from the interfaces by doing thermal anneals. And when you use CDS zinc oxide, the blue curve was the original curve, it degraded to this and it came right back. When you didn't have that interfacial inorganic layer, it never came back. It was here and just went to here. It never came back, never came back. Because the iodine had gone and affected the aluminum. It had corroded the aluminum. When you have ions present, you have to worry about all of these different effects. That's why it's nice to have a material with few ions. This one just explains, saying you have ions, then you created more ions, and then the negative ions are going to go towards the positive contact, which is the N-type. They will go through PCBM and attack aluminum. But if you have CDS and zinc oxide, they cannot attack aluminum. Inorganic contact layers are great. They prevent ions from affecting your metal contacts. So to summarize, the perovskite solar cells are a promising technology for tandem cells with silicon. Everybody wants 35+% efficiency, everybody, because the solar cost will come down by another 50-60%. But there are major problems, such as thermal instability and degradation under light, as well as interface-related degradation, and they remain. The economical PV generation, the material must not degrade. It must not degrade greater than 30%, 10% over 30 years. Silicon, good silicon solar cells guarantee 10% over 30 years. Not all. There are many solar cells in India of uncertain parentage, which, in other words, people took shortcuts that are degrading a lot more, but the best ones are degrading 10% over 30 years. And they must be stable at temperatures exceeding 100 degrees centigrade. I already told you they measured 86 C at 40 degrees ambient, which is 96 C at 50 degrees ambient. Perovskite do not meet these requirements. We need more research. We need inorganic perovskite that do not thermally degrade, and we need to minimize the number of ions. And the material needs to be non-toxic and insoluble in water. The lead perovskites are toxic and soluble in water. We got to get away from that. Hey, that's what research is. You guys have the opportunity to do that. The field is open to you. You are going to make the progress. I'm not going to make the progress. It's up to young people like you all over India who have a great opportunity to improve the material, to go to non-lead materials, to go to materials where the ions are very stable, they're not breaking down by light, and make efficient materials which will last a long time, which are also environmentally stable. Thank you.